So now I would like to discuss the answer to our question. So the question was, you have like many single phase rectifiers are connected to three phase system. So here you can see like three identical rectifiers connected to the each phase. So we have the L1 and the neutral of the L1, and L2 is the neutral, L3 and the neutral. All neutrals are connected in the grid. So this is like a typical power arrangement in your house. So from one of the plugs you have 230 volts line to neutral. You know, that can define like different rooms in your buildings or different houses in your apartment, you know, that kind of thing. And now we would like to calculate the neutral line. And for load, again, for simplicity, assume you are supplying a very large inductor which can be modeled like a current source. Let's say we have a current source, okay, and let's say again for simplicity, this is, let's say, ID, that is equal to 1 amp, and let's say every current draws current at 1 amp. So of course you have like 120 degrees between those phases, so you have balanced current, and of course this is a rectifier, so this is DC on that side. And what we will have on the grid side is, if you remember it from the previous weeks, we will have basically a square waveform, but all those square waveforms will be shifted 120 degrees. So the question is, what should be the net IN, right? So if you have I1, and it will be the same current from here, plus we will have the I2 going through here, we will have the I2, and then we will have the I3. All those things will be equal to our neutral line current going to the transformer or your building or whatever. Then what should be the IN? I mean, the first thing says, you have all equal currents, they are 120 degrees shifted, then they should cancel each other. Maybe you can say that should be equal to 0, but that is wrong. I mean, that is only correct if you have a pure sinusoidal current at that side, okay? And in order to have pure sinusoidal current, you need to have a pure resistive load at the secondary. But in our case, we have an inductive component, and if the inductive component is large enough, so we can model it as a DC source or DC current, as it is difficult to change the magnitude of the current in the inductor. So I will calculate in two ways, okay? I would like to calculate. So I will calculate it in two ways. So let me remove me. So you have either geometric or trigonometric calculations. Let's do it with using the trigonometric waveforms first. So what you have from I1, okay, let's say I1 is equal to a square wave, right? The magnitude is 1, this is 1 amps, and you will have minus 1 amps. And I2 is 120 degrees shifted for that one, I3 is 120 degrees shifted from the other one. So let's write that waveform. If you again remember from the Fourier series, I will have the 4 over pi component of the fundamental, okay, this is 4 over pi of the first component, then I will have the third component, then I have the fifth component, and it goes like that. So let me clean that part a little bit, and let me represent I1 using the Fourier series. So for that I1, right, is equal to, we have 4 over pi for everything, and then I have the sine omega t plus 1 over 3 sine 3 omega t plus 1 over 5 sine 5 omega t, and it goes like that with the 7th, 9th and so far. Then I will have the I2. Okay, I2 is the same one, 4 over pi, and I have the sine omega t, okay, minus 120 degrees or 2 pi over 3, and plus, okay, but the important thing is, if you remembered from last year, when writing that one, that time component is also multiplied, so it becomes 1 over 3 sine, okay, 3 omega t minus 120 degrees, right? Because it's also multiplied with that one, plus 1 over 5 sine, let me write it here, plus 1 over 5 sine 5 omega t minus 120 degrees, and so on. And for I3 I can write the same thing. Oops. I can write the same thing, 4 over pi sine omega t minus 240 degrees plus 1 over 3 sine 3 omega t minus 220 degrees plus 1 over 5 sine 5 omega t minus 250 degrees, and it goes like that. So if I would like to calculate neutral current, I will add all those together, right? I will have all those together, which will give us the neutral current, right? So what happens for the first component? So I have omega t minus 120 degrees, omega t minus 220 degrees. If you remember the phasors, so that is equal to adding like 3 vectors like that. So this is sine omega t, one of them is 120 degrees, the other one is minus 240 degrees. So basically, if you add all those up, it will be equal to each other, and they will all cancel each other. So the first components, that one will cancel each other. So you will not see any first harmonic component, any 50 Hz. If this is a first 50 Hz grid, you will not see any 50 Hz component in that one. So let's see how does it work with the third component. So the third component is quite strange. So we have 4 over p, and we will have all 1 over 3's as well. And let's write in the long form, we have sine 3 omega t, right, plus sine 3 omega t, this 3 is going to be multiplied with that one, that is coming from the Fourier series as well. So it becomes 3 sine 3 omega t minus 360 degrees. Of course, maybe I should write it in minus 2p, but it's the same thing. So, and then last one, 3 omega t times 3 times 240, so that is plus sine 3 omega t minus 720 degrees, right? So for that one, the interesting thing is, if you just remove minus 360 is the same thing, and minus 720, they are the same thing. So we have basically not canceling each other, but we have 3 of the same component, and they are not canceling, but they are adding up. So you have 1, 2, 3, and there's 1 over 3 here, so it suddenly becomes 4 over p times sine 3 omega t, right? So then that means we have a frequency with the 3 times of the 50 Hz. So this it is a 150 Hertz component. Okay, so let's see how does it work for the fifth component. So for the fifth component, I have, again, I'm not writing 4 over pi again. I have 1 over 5, times sine 5 omega t, okay, and plus sine 5 omega t minus, okay, 5 times 120 degrees, it is 600 degrees, okay, is that one, plus sine 5 omega t, and if you multiply that one with that one, it is minus 1200 degrees. Okay, so how does it work? So let's think. So I can add 360, or I can subtract 360 or the multiples of 360. So let's add plus 720 degrees to that one, just to simplify it, and that thing can become plus 120 degrees. All right, and I don't know if you just add what is the next multiple. Let's say let's add plus 1080 degrees. Okay, so this will become minus 120 degrees, or that can be written as minus 240 degrees. So we have still, the order of those phasors are swapped. So now the original one is at 0. Okay, we have that phasor. So then we have a 120 degrees component. It is like that. It is like that. And we have the other component at positive 120 degrees or minus 240 degrees. It doesn't really matter. But at the end of the day, they all cancel each other as well. So the fifth component goes as well. Okay, so we have third component, and you can do the same thing for the seventh component, and you will see it will cancel itself. And the interesting is, if you do it for the ninth component, you will see it doesn't cancel itself, but it will become like, again, 1 over 3 sine 9 omega t, and so on. Okay, so it will have only multiples of third harmonics. Okay, and if you look closely, I mean, if you now think 3 omega as your new harmonic component, so that becomes the fundamental component, and this becomes the third harmonic, and the other one will become the fifth harmonic, and so on. So this is basically a square waveform. Okay, this is a square waveform, but with the 3 times of the frequency. So the line harmonics, the neutral line harmonics, will be a square waveform, but not at 50 Hertz. It is a square waveform at 150 Hertz. Of course, it is much easier to show it geometrically. Okay, so let me bring me. So again, this now, third harmonics adds up, fifth harmonic cancels itself, seventh harmonic, if you do it, you will see it will cancel itself, and then ninth harmonic, it will also add up similar to the third harmonic, and all those harmonics will add up, so you will see a square wave here. And this is, much easier to show geometrically, but I want you to see it with the difficult way, using the harmonics first. So now let's do it geometrically. Okay, so now I would like to draw, let's draw if I can Okay, so this is the second phase, and let's say this is the third phase. So let's say this is I1, this is I2, this is I3, right? And for let me try to draw it nicely. So let's say you have a square wave like that, right? So, and in the second one, let's use a different color. Let's use the blue one, and let's say, you know, that is 2 ticks. So this is 180 degrees. So this is 60, 120, and so on. So let's plot the second one. So the second one is shifted 120 degrees. So let's start it from here. So now it goes up to here, right? So now that one is shifted 120 degrees. Let's use the I3 and shifting even further. So let me use that ticks. So I am shifting it by 2 times. I mean, I think if you just use a graph paper, it will be easier. But anyway, so now, you know, you have, let me draw that part as well. So this is IA. If you shift IA 120 degrees, or I1, if you shift 120 degrees, you have I2. Then if you shift it again by 120 degrees, then you have the I3. Okay, so it is somewhere here. So now I would like to calculate the total current, or in other words, I would like to calculate the neutral line current. Let me try to draw it here, right? And that will be IN. So IN, again, remember, this is 1 amp to minus 1 amp for each of those things. So I would like to add all those things. So let me put ticks here, and another tick here, another tick here. That one is I think here. It goes like that. Anyway, so first I have 1 amp. So remember, IN is equal to I1 plus I2 plus I3. So I will add all these three together. So here you have 1 amp and you have minus 1 amp. So you have 1 amp here. So 1 minus 1, they cancel each other, but we have 1 amp at here, right? So this is 1 amp. And I come to the second one. So I have 1 amp minus 1, they still cancel each other, and now I have minus 1 here, 1 minus 1 0, there's one other one, minus 1, so it goes to minus 1, right? And in the second one you have 1 1 2 and minus 1, so it makes 1 amp, so it goes like that. I think you see the picture. So now I came to here. So here I have minus 1 1, they cancel another minus 1, so it comes back to here, and you can start doing it yourself, and you will see this will be the shape of neutral current. Okay, if they are like 50 Hertz square waveform, this is a 150 Hertz square waveform. I mean, that is kind of important, and that actually shows us why, you know, THD is important. So even if you have balanced, you know, 120 degrees shifted currents, that doesn't mean the addition of that thing will be equal to 0. Actually, yes, 50 Hertz component cancelled each other, but the third harmonic components are adding up, and you see actually the same magnitude. It is 1 amp to minus 1 amp at 150 degrees, and you can have the fundamental component of that waveform, right? And that fundamental component is 4/pi sine 3 omega t, and you can have the third harmonic component of that thing, so on. So basically you have 150 Hertz, let me write, so it is 50 Hertz times third harmonic, ninth harmonic, after, so we don't have the even harmonic, so it is 15 harmonic, so on. So in the neutral line current you will see 150 Hertz, and that will be the most dominant case, right? And then if you have 450 Hertz component, and I think this is 750 Hertz component, so on and so on. Okay, so you are basically injecting some high frequency components to the neutral line, and that can affect other customers. Okay, so let's see, you know, those effects. So you could have the voltage waveform notching, which I will show you a couple of slides. So next you will have, you know, some neutral line current. Those neutral line currents is now, I mean, if you think about that thing, why neutral currents are, yes, you have some resistances and inductances of the line, right? So, and this is J omega L, and let's say this is your home and you want to have like 230 volts line to neutral. So whenever you are injecting some high frequency currents here, I neutral, so because J omega L is increasing with the higher frequencies, the potential of that line will go up. So you will not have 0 volts, but you will have a higher point voltage at that point, you know, even if you are using balanced current, and that can create some problems in, you know, safety both of you and also for your equipment. And next you will have the THD problems. Remember, the THD is usually limited, you know, for 5%, 8%, whatever, and the THD of the square waveform was 48 something percent, and that is why, you know, if you have a high THD, then it will create some problems in your grid. So this is a more realistic case. So you can have some, I mean, this is not, again, in our case we are just drawing a square wave current, but remember, if you have some kind of capacitors or some kind of voltages at the secondary side, then even the current will not be continuous, so you will have some peaks with that thing. Okay, you will have 0 regions, then you will have negative regions, and if you have that kind of things, then of course you will have the fundamental component. The fundamental component will cancel itself, but again you will have the third harmonic component, and they will add up, and you will have distorted current in the neutral line. And in Mohan there are some detailed examples on that one. Another important one is the line voltage distortion. So whenever, I mean, it doesn't have to be like for 3 3 rectifiers on separate lines. You can have the same effect just with a single rectifier on a line. So if you have capacitors and resistors, whatever, you are basically drawing not a sinusoidal current. It can be a square current as in an inductive load, or it can be like some kind of peaky current like that, right? From here, whenever you are drawing that kind of current and it doesn't have only the fundamental component but the high frequency components, then this is, for example, this is your home, right? This is your home and this is your neighbor's home. So let's say you are connecting a large rectifier and you are drawing 100 amp, whatever, you are drawing quite a lot of power, and then there is some inductance. I mean, you are connected to the same grid, but there is some inductance due to the all the cables bringing the power to your home, and from your neighbor's home to your home there's also some separate cables, and now you are drawing here some high frequency components, and due to that high frequency components there will be some large voltage drops here. So because of that voltage drops, basically the power connected here will see some distorted voltage. So they will not see some sinusoidal voltage, but there will be some distortions on their voltage source, and it can affect their power quality and that kind of things. Usually it's not problem for your for domestic appliances, but assume this is one factory and this is another factory, and if the factory is, if you have some critical equipment, that can have some kind of noise from the neighbor from that effect. So on top of the industrial connections, so in your domestic homes, if you just look at the electric meter, they are just measuring how many kilowatt hours you use. So they send you a invoice depending on your usage. But on industrial applications, they are checking for power factor. So you need to have some kind of compensation. You can't draw like too much inductive or capacitive current, otherwise you have to pay a fine. And actually we discussed those things on the third year. And on top of that, they also measuring the THD. So what is the current harmonic? So if you connect that kind of harmonic inducing equipment, it is your responsibility to put on proper filtering, so the harmonics that you generated is not injected to the grid and it is not affecting other people's equipment, right? And here you see a more realistic neutral line current. If you not a perfect current source, but if you are drawing some inductive load, so if you are drawing some supplying some RL load, maybe an electrical machine, DC machine, or lightning, I don't know, then it will not be a perfect DC, and this will not be a perfect square waveform, but still, as long as you have the third harmonics, fifth harmonics, seventh harmonics, the Fourier coefficient can be changed. So basically fifth and seventh components are cancelling each other, but the third harmonics are adding on top of that one, and you can see this is your supply voltage, and this is the fundamental is the third component. So whenever this makes one cycle, that one makes 1, 2 and 3 cycles. Okay, so the most dominant one will be the third harmonic. So when you are designing that kind of circuits, you need to be careful about how to cancel the third harmonic components.